And welcome back, students, as we get into our second lesson on patterns and sorting. Today we're going to discuss two of those patterns, merge sort and quick sort. So this is going to build off of what we talked about last time. So to begin, let's start with the merge sort. So the simplest visualization of the sorting pattern we discussed in our previous lesson is, of course, the merge sort. Now the example merge sort and its demo merge sort demo can be found in our class materials. In this realization, the array base type is specialized to the type double. The merge sort is therefore an example of with the definition where a split is pretty simple. You have the first half of the array and the second half of the array. It's just going to divide that array into two intervals with no rearranging of the elements. It's just going to say, hey, I'm going to cut it in half, and we're going to look at those two halves. Now the join method, of course, is a little bit more complicated. So after the two subintervals are sorted, the method join merges the two sorted subintervals, copying elements from one array to a temporary array. The merging starts by comparing the smallest elements in each smaller sorted interval. The smaller of these two elements is the smallest of all the elements in either subinterval, so as to move to the first position in the temporary array. The process is then repeated with the remaining elements in two smaller sorted intervals to find the next smallest element and so forth. So there is therefore a trade-off between the complexity of the method split and join. You can make either of them simple at the expense of making the other more complicated. So if you have a very simple split method, you're going to have a much more complicated join method. If you make your join method really simple, your split method will be very complex. So in looking at our merge sort, you're going to see, well, split is pretty simple, and the join method is a lot more complicated. Next, we're going to examine the opposite, where the split gets complicated and the join is simple. All right, and that's the quick sort. Now, before we go and look at this, let's just quickly take a look at that code here for merge sort. In here, you'll see right here is our actual sorting, and we have recursive calls here for sort and join. So if we look at split, this is it. One line of code. It's really simple. It's just literally taking the array, cutting it in half. But here, if you look at the join, there's a lot more to it. Right? That's because it has to go in sort that array completely. All right, on those two pieces, compare them, see which one's smaller, etc., etc. All right, when we look at quick sort, like I said, we're going to see the opposite. You'll see my split is a lot more complicated, but then the join, in this case, says nothing to do. Right? It's very simple, and let's explain that here as we look at quick sort. In our quick sort realization, the definition of split is quite sophisticated. If you notice, it's almost about the same length as our join method from before. Now, in this case, an arbitrary value of the array is chosen. This value is what's known as the splitting value. It's not picking necessarily the first or the last, it's just picking kind of an arbitrary one at random. So in our realization, we're going to choose a of begin as the splitting value. But really, any value will work equally well. It could be the first value of the array, it could be the last value of the array. Doesn't really matter. So then the elements in the array are rearranged so that all those elements that are less than or equal to the splitting value are in the front of the array, and all the values that are greater than the splitting value are at the other end of the array. And the splitting value is placed such that it divides the entire array into these smaller and larger elements. You also know that the small elements are not sorted, and the larger elements are not sorted. But all the elements for the splitting value are smaller than all the elements after the splitting value. The smaller elements are sorted by a recursive call, and the larger elements are sorted by another recursive call, and then these two sorted segments are combined with the join method. In this case, our join method is as simple as it could be. It does nothing. Right? And because of that, the sorted elements all precede larger sorted elements, so the entire array is sorted. So just by doing a split, it gets sorted. So let's ask ourselves then, do we need technically a second array? So because both our merge sort and the quick sort realizations can be done without the use of a second temporary array, technically we can do that. However, in doing so, that detail would only distract from the message of this example that we're looking at. In a real application, you may or may not, depending on the details, want to consider the possibility of doing a sort realization without the use of a temporary array. All right, so obviously we have some more sorting methods here. In the past, we've discussed things like bubble sort, selection sort. Now we've added to our repertoire merge sort and quick sort. So there are obviously some restrictions on our sorting patterns. I think that an N got lost here. not pattern. Should be an N there. The sorting pattern, like all patterns, has some restrictions where it applies. As we formulated our sorting pattern, it applies to only types where the less than operator is defined. It also only applies to sorting into increasing order. It does not apply to sorting into decreasing order. This is a result of simplifying details in order to make the presentation clearer. So we'd have to do a little bit of work for sorting, instead of just going greatest least to going least to greatest. You can also make the pattern more general by replacing the less than operator with a Boolean valued method called compare, which has two arguments, the base type of the array, which returns true or false, depending on which comes first for the second. Then our only restriction is that the compare method must have a reasonable definition. This sort of generalization is discussed later in chapter in the lesson. It looks like I added a equal sign there, titled the comparable interface. So we'll look at that in the next chapter. All right, so efficiency of the sorting pattern. As I mentioned, we have 4 different kinds of sorts kind of on our belt. Essentially, any sort algorithm can be realized with this kind of divide and conquer sorting pattern that we've discussed. However, obviously, the most efficient implementations are for those which typically the split method divides the array into substantial chunks, such as half and half or 1/4, 3/4. A realization of split that divides the array into one or few elements and the rest of the array will not be very efficient. For example, the merge sort realization splits the array into 2 roughly equal parts, and the merge sort is indeed very efficient. It can be shown, although we will not do so here, that merge sort has a worst case running time that is best possible up to an order of magnitude. So that's pretty much asking about what is the big O runtime. So the quick sort, on the other hand, divides the array into 2 portions that might almost be equal or might be very different in size depending upon the choice of what the splitting value is. Since in extreme unfortunate cases the split may be very uneven, the worst running time for a quick sort is not as fast as that as a merge sort. However, in practice, though, most of the time that we actually use it, quick sort turns out to be a very good sorting algorithm and is actually usually preferable to that of merge sort. Selection sort, which divides the array into 2 pieces, one with a single element and one with the rest of the array interval. Now, with a selection sort, because of the uneven division, selection sort has a very poor runtime, although it does have the virtue of simplicity. And if we want to go even simpler, also we have bubble sort. And as I've mentioned before, bubble sort is actually very inefficient, even more so than selection sort. So let's look at some of those common sort algorithms. Here's this big O chart again. Just to kind of put some stuff out there to help us remember how these things look. So let's look at them, starting with our good old friend bubble sort. Bubble sort, very easy to code. It's literally like 2 looped 4 statements. However, it has a runtime of big O n squared. All right, which means that is going to grow really quickly, right, in comparison to when we look at some other ones. Selection sort also has a big O runtime of n squared. Obviously, big O of n squared is the same for both these, but a selection sort is slightly better than that of a bubble sort. And we saw that in programming 1 when we just did a simple count variable, and we looked at the number of iterations it took for it to go through in a bubble sort versus a selection sort. Merge sort is big O of n log n, and so we don't have n log n on here, but we do have a log n, so it's going to be very similar to this, and there is just a multiplier on here. So it is going to be a lot better than that of an n squared. And quick sort is big N is also big O of n log n, so it's very similar. However, in our worst case, which is very rare, it is also an n squared algorithm. But most of the time, these are going to be more of an n log n, so it's kind of curved like this. It's going to be closer to somewhere in between these 2 lines here. All right, and that's going to wrap up our lesson for today, folks. Hopefully that kind of helps give you a few more sorting algorithms under your belt in order to help make your data stores more efficient. So, until the next time.